I will talk about self-dual monopole loops. I will explain what it is precisely in abelian gauge theories and perhaps also in non-abelian gauge theories, and instantons and their possible relation to confinement. And this is the work I did with my former graduate student, Mendel Guen. First, I will describe briefly some basics about instantons in 4-dimension and describe the famous or infamous size moduli problem. Then I will go to the notion of adiabatic continuity and calculability and reliable semi-classics. Then these are of course taking place in compactified setups such as R3 times S1 on RT times T2. But about 2 years ago, I decided that it is time to graduate R4. You know, I did enough on semi-classical domains to learn something about the theory on R4. So this was my first attempt to do so. I restudied some aspects of U1 lattice gauge theory, and to my surprise, understood something new in that context. The fact that there is also previously not quite so much emphasized monopole loop size problem, and I will describe its resolution. Actually, theory resolves it for itself for you. Then I will describe these general self-dual abelian fields and the necessity of complexification of the field space. Then I will draw some analogies between instantons and self-dual monopoles. The final part of the talk is something that took me by surprise after I completed this part and published the paper. That's something I started to understand. There is this Yang-Mills theory, and there is also something called self-dual Yang-Mills theory. It's also called Chalmers-Siegel theory, which is essentially self-dual sector of the Yang-Mills theory. And I started to understand that there are some very deep connections between this construction and the one here. And I ended up constructing some interpolation between these almost integrable theory, which is self-dual Yang-Mills and Yang-Mills. And, I will talk about something new. It's a two-parameter generalization of the Yang-Mills theory. Okay, now let's start with the classical data on instantons on R4. Of course, this is well known. Instantons are essentially a solution of this self-dual equation or anti-self-dual equation for other way around, but I will almost always talk about both of them if it will be implied. It is a famous very large dimensional moduli space. It's 4n dimensional. You can decompose it as R4, which is the center of the instanton, and R plus is called size moduli, and this MC is centered moduli. It is MC is 4n minus 4 dimensional, and MC hat is this coset essentially. It's related to global gauge orientations. Never mind. There is a very elegant parametrization of the instanton. These are in terms of so-called ADHM parameters. These are a set of n spinors. These I denoted with W. You can think of it as m by 2 matrix. And you can write down the instanton solution. This is in singular gauge because computations are easier in singular gauge. In this form, you should notice that if we are looking to instanton at large distances, it reduces to this form. And you must actually remember this form from your undergraduate days, maybe even earlier, because this is the vector field associated with a magnetic dipole. But now the distinction relative to magnetic dipole is that this object here is an m by n anti-self-dual matrix, and M by N matrix, it is anti-self-dual, and it is not your usual magnetic dipole, but some non-abelian generalization thereof. Okay. Now, let me tell you about the instanton size moduli problem. In the early days, people attempted to do semi-classics with the instanton, like we do in quantum mechanics. You look to the in quantum mechanics, we look to the proliferation of the instantons, and they lead to level splitting, for example, in the case of double well potential. And with similar idea, people look to, proliferation of the instantons in 4D. But if you go ahead and write down one instanton contribution to partition function, it does something at the time looked weird. So the contribution comes about, there is this scale factor, and there is this factor coming from running. And you see that even for n equal 2, this factor, the contribution of the instanton to the vacuum energy, diverges at long distances in the infrared. And this is a big problem because it's a long distance IR divergence. It tells you that there is something you do not understand about this, about the construction. So this observation renders the naive semi-classical expansion based on instanton meaningless. However, this divergence that I mentioned here, if you go to semi-classically calculable domains such as R3 times S1 or R2 times T2, which are, in theory, is adiabatic connected to R4, this problem doesn't exist. So in these cases, if you have an instanton with size moduli larger than this, and you will have, they will all fractionate. And you can see this very explicitly. And they fractionate to either on R3 cross S1 to monopole instantons and on R2 times T2 to vortex instantons. Let me just in a slide tell this adiabatic continuity idea. Normally, if we start with a theory on R4 and compactify one direction for a long time, at least in the QCD community, this was interpreted as a thermal circle, and there is a phase transition. Despite the fact that by asymptotic freedom, the theory gets, weakly coupled in the small circle, you do not gain much because, you learn about phase structure of theory, which is wonderful, but for my purpose, it is sort of detrimental because by studying small S1, it is hard to learn something about large S1, because there is a phase transition. And it is understood that, you can construct theories in which there is this continuity between large circle and small circle. Of course, this was very well known, widely known in the context of supersymmetry. All supersymmetric theories naturally satisfies this. But also, all non-supersymmetric theories were famously not satisfying this. But then, we came up with many non-SUSY theories with better judiciously chosen boundary conditions, crucially non-thermal, where this idea holds. And you can also make it work not only R3 times S1, but R2 times T2. And just in conjunction with the earlier part of the conference, this is intimately related to this idea of large and volume independence of Eguchi and Kawai. Which one?
The thermal one.
Yeah, gauge coupling becomes weak by asymptotic freedom, but of course long distance is not weakly coupled. It's obviously. Okay, so this works on semi-classical calculability on R3 cross S1. They started some time ago, but then there was this point where we started to examine R2 times T2. To be honest, I thought it was a retrograde. It was a step back, and that was the reason I wasn't working on it. But Yuya, when we were discussing, showed me that there are some new phenomena, new perspectives, and it reveals something deeper about the instantons. Hence, we started to work, and Yuya and Yui Hayashi worked it a lot in this context. And the very important fact in these cases is that the semi-classical expansion parameter in these cases is not the instanton factor, but it is instanton exponential of the instanton factor divided by n. And the semi-classics is reliable provided this ln less than lambda inverse. So as I said, semi-classical expansion is an expansion in these fractional instantons or their clusters called bions. And again, as I said, these regimes are adiabatically connected to R4 in the sense of gauge invariant parameters, but it doesn't mean that you can take the effective field theory and extrapolate it to large circle. Effective field theory has a region of validity. It is valid provided this condition holds, and beyond that, you cannot continue these things to larger circle. You cannot continue your construction. Then you are not talking about, what you want to talk about, This is just for the old times memory, just an example of what happens. For example, if you take SU2 gauge theory with adjoint matter, okay, you have instantons for the instantons, which are self-dual, as well as monopole instantons and KK instantons, which are self-dual. And you have these objects with magnetic charge and half a topological charge. And then you can construct these BPS KK bar type object, which has magnetic charge 2, but topological charge 0, and even these neutral objects. And you can actually, when you write down the superpotential in n equal 1 super Yang-Mills theory on R3 cross S1 and build the bosonic potential out of it, they describe these objects, these composite objects. You can show this. And hence, that means that the semi-classics is based on these objects, and you can write down effective Lagrangian. So far, so good. So what happens with the size moduli problem? With the size moduli problem, okay, the big issue was this integrand, okay, was growing very large. It was lambda rho 11/3 n divided by 3 minus 5. It's growing like that polynomially, but at n large, it grows even faster. But what happens with these semi-classical constructions is essentially following. If you have a small instanton up to the size of Ln, still this function grows in the same manner. But after that, the gauge coupling, there is SUN gauge structure reduces to something like maximal abelian group, something like U1 to n minus 1. And there are no charged degrees of freedom which would make the coupling to run further. So coupling, in some sense, freezes. This is similar to a generic point in the moduli space of Seiberg-Witten theory. And then the size module, this integral decays, and the integration is finite, and the IR divergence does not even exist. Okay? Now, okay, some remark here. Now trying to go ahead.
Just to be sure I understand. So this picture is only when ln is much smaller than 1.
Exactly.
Okay.
Yeah. Otherwise, it will continue to grow, obviously, and the theory will become strongly coupled, and you will lose control.
You don't trust it.
You don't trust it. Now, this is all nice. The previous story, it's all nice, but unlike these weakly coupled calculable domains, there is no physical fractionalization for sure. For the instantons on R4 in gauge theories or instantons in sigma models like CPN, Okay. So what is happening with the instantons on R4? Okay. But even before this endeavor of weakly coupled, semi-classical domains, people like, especially Van Baal, Li, Lu, and Piljing constructed compactifications either in the context of Yang-Mills theory or in the context of string theory, N equal 4 super Yang-Mills, where they show that, in a non-trivial holonomy background, if your Polyakov loop is non-trivial in the compactified direction, there is a fractionalization to these constituents. They didn't build a semi-classical theory of mass gap or confinement based on them, but they knew fractionalization very clearly, very cleanly. And some similar observations were made by numerical studies by Gonzalez Arroyo. So what does this mean if we think about it? If we think about it, it means that whatever is the internal structure of an instanton on R4, when you compactify it, it must be able to accommodate either these n types of monopole instantons or n types of center vortices. These in 2 dimension, these reduces to vortices. Of course, center vortices are point-like in 2 dimension. And as I said, with Yuya, we established a nice semi-classical description of them. And it is a little bit weird. They must have some internal structure, but it doesn't reveal itself on R4. Okay? So, and I wanted to understand better the instantons on R4, and we wanted to understand them better. I will give you one more classical data about the instantons, which is extremely important. And so it is as important as ADHM, description of the moduli space, because it's also classical data on the same footing. So if you take two small instantons at a large separation, or instanton anti-instanton, and look at their interactions, the instanton-instanton interaction is strictly zero because they are a BPS. Okay? But if you look to instanton or take this formula, if you look at it, it is of type 1 over x to the 4, which is long range, algebraically falling, but it is falling much faster than 1 over x squared, for sure. And there is this structure, and this structure is, again, something familiar. If you were to write down this thing in 3 dimensions, okay, you would get from your electromagnetism book 3 P1 dot n, P2 dot n minus P1 dotted with P2. This is literally dipole-dipole interaction, but generalized to 4 dimensions. That is, to my mind, very curious, because if we want to get in 4 dimension, and this is also first derived, again, this paper I mentioned, Kalan, Gross, and maybe Dashen. And in the general, however, this formula is also true for SUN in all cases of n. So when you think about it, one question, why? The reason is, we have instantons. We thought they were point-like objects in space-time. Yes, they are different from instantons in other theories because they have a size moduli, right? But where did this structure came from? This structure is something you can affiliate in 4 dimension with loops, with currents. So if you had, for example, 2 current loops in 4 dimension, you can write, of course, in 4 dimension, magnetic dipole moment is a second rank anti-symmetric tensor. You can write this thing. You can calculate the interaction between these loops, and they will decay exactly like this. But for us, instantons were not loops. To me, this is very surprising. This is very weird. Okay? But I must add one more thing. Yes, it is so, but we cannot be too naive about this standard current interaction. For example, if you take two instantons, the interaction must be zero. Whatever you do with dipoles, regular dipoles, you can never make the interaction zero. You know, maybe once in a while, in some angle, there is some accident. I don't know, okay? But for instanton, you cannot make it zero. So it cannot be just regular loop. It is for sure, okay? This is zero, and how do we reconcile the fact that, for example, instanton anti-instanton interaction is exactly like this, while instanton interaction is strictly zero. And as I said, it is very important to keep in mind that both this data as well as classical moduli space are classical data about instantons. They are on the same footing. But you know, if you look to generic review on, for example, instantons in supersymmetric gauge theories or something like that, you will never see this information. Maybe in QCD-oriented reviews, there is this formula, but for SU2, okay? Now, the question I want to ask really, what's an instanton really on R4, okay? It's a very basic question, you know, but I think it is, I put this question mark intentionally there because we do not quite understand it. What is the internal structure of it which gives rise to all these different semi-classical, you know, constructions, semi-classical configurations, okay? I will return to this question. This is my target. But first, I want to say a few things about a theory of loops, a well-understood theory of loops, and the fact that the size moduli problem may very well be fake. It is and maybe a little bit provocative statement, but you will see what I mean. And maybe more appropriately, it is an artifact of what we did. Maybe in reality it doesn't exist. So let me show what I mean, okay? I will take one of the best studied models in 4 dimension. It is not on R4, it is on Z4, okay? It is U1 lattice gauge theory with compact gauge field. I use Whelan formulation because Whelan formulation is much more useful for computations. You can do many things exactly. There are beautiful works about this, and they are actually solved quite nicely, especially in quite some detail. Polyakov mentions it in passing. You see that he understands everything, but it is like half of a paragraph, really. And there is this extended nice paper by Michael Peskin. And there is this gauge action. So when we do partition function, we integrate over these gauge fields, real valued gauge fields, and we sum over all of these integers. These integers encode the information about monopoles. They encode information about discrete magnetic flux, mu nu. Actually, we can describe this object, and it will be the current associated with the word lines of these objects, which is very nice. Big achievements, in my opinion, of Michael Peskin, this is that at least in the strong coupling regime, he was able to dualize this theory rigorously. And he obtained a lattice abelian Higgs model where the matter fields are monopoles and the gauge fields are dual photons. It is like, in some sense, like a bosonic truncation of Seiberg-Witten construction, basically. There is a little bit less matter here than there, okay? this is very nice. So what do we learn from there? So if you work out with these currents, and you can take the current and make a Hodge decomposition of it. You can actually write this thing, partition function here. Sorry, it doesn't go back. It's okay. It factorizes to a photon part, dual photon part, and monopole part. And the monopole part is actually a classical gas of loops interacting, where loop segments are interacting with each other by this 1 over x squared interaction, as they would do in 4 dimensions. And I decompose these following Peskin to G, some G hat and G naught. And G naught is the self-energy of the loop, which we will associate with the mass of the monopoles. Okay? You can go ahead, write down a scalar QED, abelian X model. There is dual photon, and there is this matter field. You can actually derive this formula from, from the word line representation of this lattice model, a scalar monopole coupled to dual gauge field and incorporating some potential. And most things in this model, as I said, are very well understood. Okay? So you can ask, why am I talking about it? I already alluded. The reason is very likely the second most important lesson emanating from this U1 lattice gauge theory are not discussed earlier in literature, and they may shed light on a problem in pure Yang-Mills theory. Okay? So you can study phases of this theory. People study it. It's strong coupling. These monopoles proliferate. That's equivalent to condensation of the dual Higgs field, this dual superconductivity that people talk often here. But if you go to weak coupling, there are still monopole loops, but they are very dilute, they are very heavy, and there is a phase transition at some critical point. I want to describe for you this phase transition in a very physical and intuitive and beautiful explanation by Peierls type argument. You can think about, the weight factor of loops of length L. Take a loop, arbitrary loop of length L. Of course, it is Boltzmann suppressed as mass times length of the loop, and you would think that it is not quite relevant. But then you have to count how many loops are there, how many non-backtracking loops are there, starting at some point, going around making L steps, and coming back at the same point. If you count this, this gives you the entropy factor associated with these loops. And to my surprise, you can do this counting quite precisely. It is, roughly speaking, 7 to the power L, which is something growing exponentially with size L. And you can put a bound for the C between these two numbers. This 7 is really coming from, 2D minus 1, the fact that we are in 4 dimensions. And this is something well known in lattice community, also graph community. So good. Then this argument tells you that if you are at strong coupling, E square very large, this entropy factor dominates and loops proliferate. If you are at very weak coupling, Boltzmann factor, energy dominates, and you are in the Coulomb phase. These are the two phases of lattice gauge theory. What is there to learn? Well, okay, I mentioned these are the two phases. You can also construct the same thing in U1 abelian Higgs. And let me skip this, it's not that important. The important thing is following. Let's take, again, we are in the context of U1 lattice gauge theory, take these two monopole loops. And let me call the current K as magnetic current. These are my currents, and this is the standard current-current interaction. But let me take them far apart. I already gave the answer, but if you calculate this, go ahead, calculate this, you will find this dipole-dipole interaction, which is very nice. Now, what is the problem? In Yang-Mills theory, based on the fact that small instantons at large separations, exactly same calculation, interact by this 1 over x to 4 potential, it is argued that, oh, this is much weaker than Coulomb potential, which is 1 over x squared. Hence, it can be ignored despite it being long range. The lesson we learn from semi-classics, one should never ignore long-range interactions between topological configurations. Okay? So this is the same situation with monopole loops. So let us do what we did exactly in the dilute instanton. Yes, let us ignore the interactions between loops, and look what happens. So this was my moduli size integral, but now I want to calculate one monopole contribution to the partition function. So I have to sum over all possible lengths of L with all starting points, and all starting points will give me some volume of the lattice. But the summation over L, if you look at it, whenever you are in the strongly coupled regime, it's an integral of exponentially growing function. It is much worse divergence than in Yang-Mills theory. So this is clearly divergent. So this is when you do non-interacting, yes. Clearly, this is nonsense. And when we construct dual abelian X model, it has no such problem. So what is the error? This 1 over x to 4 is indeed much weaker than Coulomb, and we ignored it despite it being long range. The crucial thing, although small loops interact by 1 over x to the 4, the current bits interact via 1 over x squared, which is interesting. In the phase in which loops proliferate, it is certainly unjustified. We are ignoring 1 over x square type interaction. It is like ignoring Coulomb interaction in a Coulomb gas. You will not get a Debye length, period. Okay? This is essentially, in my opinion, what happened in the first semi-classical attempts with instantons in Yang-Mills theory. However, the difference, crucial difference in Yang-Mills theory is that we do not know the counterpart of this underlying 1 over x squared type interaction, or what gives rise to it. This is the thing that we do not know. Okay? Go ahead.
Current beats, you mean J0, like the charge density?
No, it's current segments. Think of it,
segments, yes.
Current segments.
When you found these closed loops, isn't there also a prefactor L to some power?
Oh, it is, there is, of course. Apart from, very good, apart from the most basic one, choose a loop. You can say, I started here, end up here, there, but you can also say, hey, I started here, end up there. You have to divide at least by L. But that exponential factor is there for these non-backtracking loops. I actually communicated with some mathematicians who were doing these kind of things, and I put this upper and lower bound after discussing with them. Of course, it's a very, very, very beautiful argument, and it's always extremely useful. Now, okay. I also want to say one more thing about R3 cross S1. R3 cross S1 also tells us something aligned with this. It cannot prove anything about R4, but it has to be consistent with whatever is emerging on R4. Indeed, as I said, instanton splits up to n monopole instantons, and these are monopole operators. If you are in the Polyakov model, you can forget this part because it is gapped. But in general, monopole operator is this. There is a complex field in the exponents. It's very important. And an instanton is essentially putting these monopoles together, okay? And indeed, the classical interaction between monopoles and anti-monopoles are carried with this phi and sigma channel, and both of them are 1 over x. But if you look on the other hand, these were charge operators, but if you look to instanton operators, you see something interesting. Again, this is on our 3 cross S1. Let's say you take 2 monopoles, at x1 and x2. Let's say they are centered at some x center, and the distance between them is d. You can just do a Taylor expansion on this, and you will see that instanton operator is actually, on our 3 cross S1, is some sort of a dipole. It's actually not a very standard dipole. This part is a standard dipole, but this part, if you want to interpret it really, it has to be an imaginary dipole. And I will come back to this. Don't confuse yourself about this if this part sounded confusing, but there is clearly a dipole there. Now, I wanted to put this thing because, you know, this also inspired a little bit from Polyakov's. He likes this analogy as well, but I will use it slightly differently. You know, this cave allegory. There is this very weird object, instanton, we do not understand, but we are people trying to understand some of its images, some of its reincarnations. And on one wall, we were understanding monopoles, then came Yuya, and we started to understand the other wall. And they don't look much alike, but now we can continuously connect them. And whatever this is, you know, once we understand it, we know that its images, its shadows must reproduce those. Okay. Let's call this mother theory, okay, you know. And then, therefore, my goal is try to understand something directly on R4 or Z4. Now, somebody said that in vacuum of the Maxwell theory, there are no instantons. There are no, you know, non-trivial self-dual configurations. However, in abelian gauge theory, I am taking a Euclidean setup. It's trivial to construct self-dual fields. Turn on some, pay attention, it's Euclidean, current K and current J. So if you take these sources correlated like this, you know, it is like double loop. The field is automatically self-dual or anti-self-dual. And naively, you know, and these fields are actually nothing but the instanton field strength, okay? It's very interesting. Now we are in abelian, okay? Now, naively, if you, one more thing before. And if you look to interactions now, you did something correct now. If you look to interactions, these things are vanishing, self-dual are vanishing. You can show this, and self-dual, anti-self-dual has this form. And it has the same form as instantons. Now, we can think of n squared minus 1 components of Maxwell field, viewing them as components of a matrix. And we can actually reproduce large fields of a, you know, the field of an instanton at large distances by putting these magnetic dipole moments coming from this current together.
Quick question.
Yeah.
So what exactly did you do? So what does self-duality impose instead of just having a monopole loop?
Oh,
What is this extra stuff?
Naively, it looks like I introduced an magnetic current and electric current, okay? But I will tell you that this is not a dione, okay? I will tell you, because this is in Euclidean, I will tell you it's Minkowski interpretation, where we do Gauss's law, you know, we live in Minkowski space. Yeah. Now, however, these things, in Yang-Mills theory, we have these dipole moments, and, you know, of course, it is self-dual. There has to be a multiplicity of 3, and there are 3 n squared minus 1 such objects. But it is something very bizarre, because all of these 3 n squared minus 1 things are determined by 4n minus 4 parameters of the centered moduli space. It is something extremely orchestrated, you know, I intentionally use this word because they don't play a game distinct from each other. They are all in harmony. They do something in unison in some sense. Okay, it's interesting. Now, Tin asked, what did I do exactly? And I want to bring this thing up. Is self-dual monopole loop a dione loop? You know, if you look at it naively, we introduced a magnetic currents and electric currents, but remember this was in Euclidean space. And actually, you can analytically continue self-duality equation to Minkowski space. It becomes this. It tells you that magnetic field is real, then electric field must be purely imaginary. So we are working in the space of complexified fields. I will tell that the self-dual version of a monopole in Maxwell theory must be accompanied by a real magnetic charge, but purely imaginary electric charge with the same magnitude. Same magnitude, it's not important. This will also guarantee that self-dual interaction is zero. So let me do my Gauss's law. Gauss's law was this for the electric charge. For magnetic charge, Gauss's law was this. And E times G satisfied Dirac quantization. I think the right setup for this problem is complex phi E, complex phi B. So now electric field, the electric charge has a component which is in units of E, which is real, the thing that we know and love. It also has a purely imaginary part in units of G, where G is 1 over E, and it's purely imaginary. Now, these are the standard things. If we have a monopole, we have some charge G, electric charge 0. But if I want to make it self-dual monopole, I do get this. However, normal dione is not self-dual. It is magnetic charge G, electric charge E. And if you want to write down a self-dual dione, you have to have these mixture, both real and imaginary electric charges. You cannot write a dione field which is manifestly real, neither in self-dual dione, neither in Minkowski space nor Euclidean space. This was the discussion for the charges. These are charge, Minkowski charge real. There is also similar discussion for currents. You know, the role of the currents is sort of flipped because in the current there is a time derivative. And there is such a structure, but let's not worry about this, okay? So now let's go back. Instantons, despite early hopes in connection to mass gap and confinement problem, are deemed somewhat irrelevant for these phenomena in the long run. It is commonly accepted that they do not play a role in confinement, large N. They are viewed as completely suppressed in large N and mass gap. So I am pushing the opposite idea. However, you know, what we understood in the last 15 years is that in all these cases, fractionalization of the instantons lead to all interesting non-perturbative phenomena, and they are not inconsistent with large N. Especially they would survive in standard large N. Now, let me pause here and ask following question. Apparently, in the story, whatever the story is, this existence of long-range classical interactions between self-dual and anti-self-dual configurations play a most prominent role. By the way, when I made this table, I thought I was sort of fooling myself a little bit, but I knew it was true. Then, now you will see the connections. You will start to see the connections. Then I recalled some conversations I had with Lance Dixon when I was a postdoc. You know, he was working on these amplitudes with, positive helicity, negative, they are decomposing gluons to positive helicity and negative helicity. And I recall that, you cannot really make a positive helicity gluon real, sort of, if you try to make it real, it will be some superposition of self, positive felicity and negative felicity. But mathematically, there is such a solution. Okay? Then I ask myself a question, this question. Let me turn off anti-instanton out of the game. Can I do this? Yes, I can. All I have to do is to insert this Dirac delta into the path integral. Insert a Dirac delta, which tells you that I must integrate over self-wall field configurations. And this took me to a big surprise, to some very interesting literature in the context of amplitudes. Lots of wonderful developments. So let's start with Yang-Mills theory, and for clarity, let's set theta angle to 0. Okay? Now, I start with the Euclidean path integral and insert this constraint, which tells me that I must integrate only over self-wall fields. Let us see what will happen. It is surprising, okay? Let us impose this by a Lagrange multiplier, and let us also write trace f square as f minus square and a topological term. Clear? Now, this is my trace f square part. I wrote it a little bit differently, and this is my constraint. Now, the very interesting thing is that you can do a field redefinition and absorb these parts, which include kinetic of the gauge fields, to the BF. Interesting. And I will take B to be anti-self-dual, okay? So it will impose that anti-self-dual part of the field strength must be 0, hence I must integrate over self-dual parts. The outcome is this. This is the theory. There is a topological term, there is BF term, okay? You can also do this integration. There is a Dirac delta which tells you that you are only summing over instantons. And there is only this topological term. I suspect this must be related to Nekrasov's work, but I couldn't come with all the details. But I wanted to talk about it here also to discuss with friends here. This is good. This action then came to realize that is something well studied. It's called self-dual Yang-Mills theory. It is introduced in the context of an equal for super Yang-Mills by Chalmers and Siegel. But now, note that this 1 over g square multiplies only topological term. If you wanted to add theta, you can add theta, but I wanted to reduce the cluster. Okay, no worry about it. And this is not a problem, since you may think that, oh, this thing will lead to a divergence. But since topological charge is positive now, this thing will give a sum over instantons. This part will be only exponentially decaying. Some structure that appears also in localization discussions. However, at this stage, I want to draw your attention to the curious fact that G must be interpreted as a topological coupling. It is not a coupling, kinematical coupling. It appears only in the topological term. The perturbative aspects of this theory are very well studied, actually. But about the non-perturbative aspects, there is almost no literature. There is a very nice paper by Losev et al., which is completely ignored. And Costello wrote something mathematical about it. It's also physical. It's quite nice. But I wouldn't call them trying to understand the theory non-perturbatively. They understand something extremely important about this theory in the instanton sector. Actually, I will tell you what they understand, okay? In the perturbative QCD context, I must say one thing. People do not even bother to write this term. They just write this part. they do not even bother this term because it's topological. It will not enter perturbation theory. Okay. And remember, BF term does not have a coupling constant. It's a classically scale invariant theory. However, there is something very funny. Topological term does not enter the perturbation theory, but in this theory, remember that we broke the parity between positive helicity and negative helicity. There is no longer a parity symmetry. So in principle, the topological term is a classically marginal term. You have to add to the Lagrangian. It may not affect to the theory. It may not affect perturbation theory, but it will affect the theory. Even if you do not add it, it will be generated. And this is what Losev and Costello showed. The perturbation theory alters the topological term. There is an exact one loop running of G if and only if the theory is considered in the instanton background. And the running coupling is 11/3 m. And this is now one loop exact. We also have an independent derivation of this, essentially mapping this problem to some NSVZ type computation. Maybe Arkady is here, I don't know. In Chalmers and Siegel, also in later literature, it's stated that if we deform the action with this G square trace P square, we of course land back on pure Yang-Mills theory, which is very good, But I do not want to do that, okay? I will do something hopefully far more interesting, and I have a good backup for it, okay? Instead of deforming the theory exactly by this coupling, which will conspire with that to bring it back to pure Yang-Mills, I will deform the theory with an arbitrary dimensional coupling, epsilon square. Epsilon square is my new coupling. And again, to my surprise, Witten, I told you I have a good backup for this. In this very interesting paper, Perturbative Gauge Theory is a string theory in twistor space, he actually constructed the same idea to bring back positive helicity amplitudes to the game because the game was based on negative helicity amplitude, and to bring them both together to make the symmetry between positive and negative helicity back again, make the theory back Yang-Mills. I constructed the same thing. I introduced this thing actually to generate a disparity between instanton and anti-instanton. Now, instanton action is still this, but anti-instanton action is this. In particular, in the limit where epsilon goes to 0, anti-instanton action diverges. It decouples from the theory, which is very nice. We are left purely with instantons. If you take epsilon over G1, you land on pure Yang-Mills theory. So this is a theory, two-parameter Yang-Mills theory, interpolating between Self-dual theory, which is almost integrable because the S matrix is classically trivial, and quantum mechanically there is only one loop contribution. And Bardeen claimed that this is related to some sort of anomaly. It's called integrability anomaly in the context of amplitudes. So it interpolates between this theory. You can ask, what is the IR behavior of this self-dual Yang-Mills theory? In particular, if you take epsilon over G to be much less than 1, we can maybe say something. Now I will tell you the other surprise. This is one loop exact. If you continue, there are corrections of the form G cube epsilon square. But the running of the epsilon is also same. So they both run in the same manner. But their initial condition differ by a parameter. So this becomes strong. This sector becomes strong once. And this becomes strong much, much later.
There are no powers of G in the function?
No, because from the perspective of epsilon, G is topological coupling. Isn't it wonderful? Yeah. But here there will be by NSVZ type computation. So in the epsilon limit, you can ask, is the theory gapped, confined? Very likely the answer to both are no. At least on our 3 cross S1, I can show it is no. And it's easy. Despite the existence of monopoles and no anti-monopoles, there is no mass gap. This is so both in self-dual Yang-Mills theory, also self-dual QCD with adjoint fermions. Since collaboration loves adjoint fermions, I had to do this, okay? And in fact, in the theory in the self-dual QCD adjoint with adjoint fermions, in the interpolating theory, it's very easy to construct the mass gap. Mass gap comes from these two factors, instanton divided by n, anti-instanton divided by n. And crucially, mass gap has this form, okay? In the epsilon goes to 0 limit, even at finite L, mass gap vanishes, confinement vanishes, okay?
How do you calculate it?
You can ask a bit later. Yeah.
On R4?
No, this is on R3 cross S1. I will make a claim on R4. So I'm actually done. I will answer that question. So both constructions, I think, the one based on the self-dual loops, as well as the interpolating theory between self-dual Yang-Mills and Yang-Mills, in my opinion, carry some glimpse of hope towards addressing the mass gap problem and confinement problem in Yang-Mills theory. I think they present at least something new. So this is all I wanted to say, and I can take questions.